All right. So let's get started. Um, so let's first review just a little bit of what we said last time we were together. There was exponential form, and there's log form. Log short for logarithmic. Okay. And so there's two different forms, and we were just working at going back and forth. The exponential form is the form that we were used to seeing. So if we have something called b to the power of x is equal to y, all right, that would be exponential form. And if we change exponential form to log form, what would it read? Log base b, so it's a subscript b, and then put the y there, it equals x. And there's the three parts, right? So b is what we call the base, x is our exponent or power, and y is called the argument. Okay. And so that's really what we said last time, and we practiced going back and forth and solving problems using that. Okay. And so we're going to jump into graphing, and so we were graphing things in exponential form, and now we're going to graph things in log form, but knowing this relationship is going to be helpful here. Okay, and so we're going to take some notes. Section 8.4. And we're going to look at log properties. Okay. And before we get into there's three main log properties. Before we get into those, let's just look at a couple graphing examples. And we're going to start with number 3 from our homework, okay? So f of x is function notation for y. So we can also write this as y equals log base 2 of x. And the first thing you're going to want to do is change it out of log form into exponential form, something you're more familiar with. And you have the three parts. You get your y, your 2, and your x. And if I change it out of log form, what do I get? I get to rearrange these three things. I get 2 to the y equals x. Okay. And with these graphs, I want you to get 3 points. And so I'm just going to make a table of values here. And usually it's easy to pick the x value, plug it in, and get y. But on this one, the way it's set up, it's going to be easier for us to pick a y value, plug it in, and get x. Because y is our exponent here. Usually x is our exponent, but now y is the exponent. And so what's happening here is the x and y are being switched. Do you remember, I forget which unit it was, but we would switch x and y and solve, and we found, when did we do that? What were we looking for? Inverse functions. And logarithms are inverses of exponential functions. And that's what we're seeing. We're seeing the x and y switch here. So let's pick an easy y value would be 0, right? If we make our exponent 0, what would x equal? 2 to the power of 0, which is 1. If we make y equal to 1, then x would be 2 to the power of 1, which is 2. And if we make y equal to 2, then we're going to get x is equal to 4. So let's plot those 3 points and see what kind of shape we're getting here. So 1, 0, 2, 1, and 4, 2. Okay. And as as we pick larger values of y, we're just going to end up getting this kind of this shape. It's increasing, but it's increasing slowly. How far can we how far can we go to the left? Can we have a negative x value? Why not? And if you look really at this right here, this expression, 2 to the power of y equals x. So think again, if can we plug in a value of y that will give us a negative value for x? And the answer is no, because the base is positive. Even if I plug in a negative value for y, that just makes it a fraction. It's still going to be positive. So we know we're not going to have any negative values. Is there any way to make x equal to 0? Is there a value for y that we can make it equal to 0? Could we even go to the left of 1, or is this where it starts? Could we get 1/2? Can we get x equals 1/2? Yeah, how? Yeah, so if I plug in -1 for y, I get 2 to the -1 power, which is 1/2. So 1/2 -1 would be right here. If I plug in -2 for y, I get 2 to the -2, which is -1/4. Sorry, I'm doing that wrong. +1/4. And so it's just going to get closer and closer and closer to the y-axis, but never hit it. And so we have a vertical asymptote here at x equals 0. So that would be our answer. That would be the graph for number 3. But before we leave number 3, I just want to relate this to the inverse. So if we swapped x and y, and we compared it with 2 to the power of x equals y, it'd be like swapping our table of x and y values, and it would look something like this. So this is not our graph in green, but I want you to see the comparison, because these are what we call inverse functions. And if you graph inverse functions, did we talk about this before? Their graphs will always be symmetric about this, or their reflections across the x equals y. And so our exponential functions, I just want you to see the relationship. Our exponential functions had a or a horizontal asymptote at the x-axis, where our log function now, because the x and y are switching, now the y-axis is going to be our vertical asymptote, and the x and y values switch. So when you graph, you only have to graph one of them, right? You don't have to graph the inverse, but I just want you to see that side by side, because that might be helpful to you. Do you want to try one more graph? How to graph E? We did look at one. I'll pull it up in our notes. I'll pull it up. Or find it. I think it's at the end here. Number 35. So what we said, E, we said last time, it's called the Euler's number, or the natural number, and it's roughly 2.7, right? But we don't want to write our decimal. We write E, just like we'd write pi instead of 3.14. And so just get values like that. Okay, that's what we said about E. I want you to do one more log function before we leave the graphing. So let's, I want you to go ahead and graph number 4. and I should be modeling correctly. So on our last one, we should be labeling at least 3 points here. So I'm going to do that 1, 0, 2, 1, and 4, 2. And you want something like this. Got a vertical asymptote at the y-axis. You find 3 points that it goes through. And it's increasing, but increasing very slowly. Any questions on the graphing logs? We're not going to, this is all we're going to say about graphing today. We're going to spend most of our time talking about properties of logs. Okay. So there's 3 main properties of logs, and they're the 3 rules that and the only 3 rules that you need to know to get around and work with logs. And I'm going to try to prove them to you the best that I can. They're not too hard to understand, the proofs. And then after you got the proofs, you don't have to remember the proofs, but you're going to have to remember the results here. Okay. So let's first make a couple definitions here. So let's let I wrote these down. I got to make sure I do it in a nice way for you, so it doesn't cause any confusion for you. Okay, so let m equal b to the power of x, and n is going to be b to the power of y. So they're both going to have the same base, but possibly different exponents. Okay. Then we could say that b to the x plus y, so it'll use our rules of exponents here, is equal to b to the power of x, finish it for me, times b to the power of y. But I define b to the power of x as m, so we could say that's m, and b to the power of y is n, so that would be n. So m times n would be b to the x plus y. Now I know you don't know where we're headed, but does that seem like a logical step there for you? Okay. So now let's change it from exponential form to log form. We talked about our 3 parts. We have our base, our power, and our argument. And so when we change it into log form, what do we get? log base b of what? M times n is equal to x plus y. Now, let's go back up to where I said m is equal to b to the power of x. Change that out of exponential form into log form, and we get what? Log base b of m is equal to x. And do the same thing with the other one. We get log base b of n is equal to y. And we have our x and our y down here, and now I'm going to change x and y to what they're equal to, their log forms, and that will be our first property that we're showing, that the log base b of m times n is the same thing as the log base b of m plus the log base b of n. And that's called the product property. Now, if you think about it, logs are always equal to exponents, always equal to powers. And with exponents, we saw right here that when we're multiplying, we're adding, right? So multiplying and adding kind of went together with our rules of exponents. And so it shouldn't be surprising that that's going to happen with the logs as well. And so a couple applications of this, we could say something like this. The log base 2 of 20 is equal to the log base 2 of 5 plus what? Log base 2 of 4. So the base stays the same on all of them. And so if you wanted to split something up, you could just think, what are my factors of 20? And well, that would be 5 and 4 could work, or 2 and 10, or 1 and 20. And that would be true. Or you could work the other way. You could say, if I had the log of 5 plus the log of 1 plus the log of 3, what would that equal? The log of 15. You multiply the 5 times the 1 times the 3. Now, on here, I didn't write a base. If I don't write the base, what's the default? 10. Good. We call that the common log. Good. So that's our first property. There's 3 properties, so now let's take a look at our next one. So we're going to let m equal b to the power of x again. And b to the power of n times x, using rules of exponents, we could say that, well, that's b to the power of x to the power of n. Because we know that if you have a power of a power, you can multiply them together. Right? That's a rule that we've used. And because m is b to the x, I'm going to replace b to the x with an m. And I get b to the power of nx is equal to m to the power of n. And we're going to do what we did last time. We're going to change it out of exponential form into log form. And here's how we're going to do it. We're going to view this as our base, this as our power, and this as our argument. If we do that, what are we going to get? Atticus, what do we get? Log base b of m to the power of n, that's our argument, is equal to n times x. So then we're going to move back right up here and take a look at m is equal to b to the power of x. Change that to log form and we get log base b of x. I did something wrong. What did I do wrong? Oh, no, okay. That's what I did wrong. I didn't put the argument there. Log base b of m is equal to x. And so I'm going to replace this x with log base b of m. And that's what we call our power rule. So here it is, log base b of m to the power of n is equal to n times log base b of m. And so what the power rule, let me write that. What the power rule pretty much allows us to do is if your argument has a power, you could take that power and put it in front of the log and just make it a multiple of that log. Or you can go the other way. You could if you have a number in front of the log, you can make it the power of your argument. So if I have 3 times the natural log of x, I have a number in front of the log. I can take that number and make it the power of x here and write natural log of x cubed. And that would be equivalent. And that's going to be helpful to us when we start solving with logs. What's the base of natural log? E. Or if I have log base 5 of 8, I could say, well, that's equal to log base 5 of 2 to the 3rd power, which is, now using my power property, I could take the power here, move it in front of the log, and say that, well, that's 3 log base 5 of 2. That's the second rule. And our last rule, if we have the log base b of m divided by n, we're going to use the previous 2 properties to help us figure this one out. I could say that that's equal to log base b of m times n to what power? Negative 1. Good. So we just move the n up to the top of the fraction, give it a negative exponent. Now, here's a product, m times n to the negative 1. So we can use our product property and say that that's equal to log base b of m, keep going, plus log base b of n to the negative 1. That's what our product property led us to do. Now we have an exponent, a negative 1 here. So we can use our power property and take that and move it in front of the log base b of n. So we get log base b of m plus negative 1 times the log base b of n. And plus a negative 1, that's the same thing as log base b of m minus log base b of n. So I'm going to just rewrite this here. So we see the final result that the log base b of m over n, when you're dividing, you're really subtracting. And that's called the quotient property. is what we're looking for. So except one of two answers. Your goal is to get one log, so you can get the natural log of 1 over x to the 5th, y to the 5th, or you could say, well, that's something to the 5th power. So you can make it natural log of 1 over xy to the 5th power. They're both good answers. Anybody get that? Where'd you get stuck then? The very beginning, okay. So remember in the very beginning, what I'm looking for is there a number in front of one of the logs? And there was right here. So that's the only thing I had to deal with, because the other logs didn't have anything in front other than a 1. So I made that my exponent of what was already there. So I had an x cubed there, so I made the exponent the -2. Then I'm using law of exponents, so 3 times -2 is -6. And then at that point, I can add these, but it's the product property. When I add them, I'm going to be multiplying all 3 of these together. And so I got it. I changed this to 1 over x to the 6th. I changed that to 1 over y to the 4th. And then I wrote it as 1 natural log, but it's the product of the 3. And then you reduce the fraction. So on this worksheet, your homework is going to be 3 graphing problems, or 4 graphing problems, sorry. It's going to be numbers 5 through 8 for graphing. And then I'm going to assign to you number 22 to 36, the bottom section. And I'll work through 1 or 2 of those down there to get you started, and show you what they're about. So on 22 through 33, they're going to say, okay, log of 4 is m, and log of 6 is n. And you're going to have to, they're going to give you different problems, and you got to write them in terms of just m and just n. And so it's going to look like this. So when I'm looking at like number 22, I'm thinking, well, 24, does that deal with a 4 or a 6? It does, right? That's actually, 24 is 4 times 6. And so log 24, I could write as log of 4 times 6, and I could split that up to log 4 plus log 6. And log 4 is m, and log 6 is n. And so that's my answer, because I got rid of my logs and I put everything in terms of m and n. That's the kind of game we're going to play. So now I picked an easy one there. Let me see if I can pick a hard one. Something that may not be so obvious. How about 36? 36 doesn't look as obvious, right? We got log of 20 over 3. And so let's see if we can get that one together. So we know that, what do we have? Log of 4 is m, is that right? And log of 6 is n? True? Okay, so I need to get this 20 over 3 somehow, and just in terms of 4 and 6 if I can. Any ideas? I would like that 3 to be a 6 if we could make it a 6. What's that? Divide by 2. So change the fraction to what? Change 40 over 6. Got my 6. And I also see a 4. Okay. So then I need to, we're doing the opposite of condensing, we're expanding. It's a fraction, so I'm going to change it to log 40 minus log 6. Now log 6 I know is n, so I'm good with that part. Log 40, got us to work with. What can we do? What would you do to log 40? What'd you say? So log 4 plus the log of 10 minus the log of 6. Now, log of 4 is m. Log of 10, we seem stuck there. Log of 6 is n. Log of 10 is what? It's 1. Good. Because our base is 10. And if I look at log base 10 of 10, and I set that equal to x or something, that's asking the question 10 to what power is 10? Well, that's 1. So now we have m plus 1 minus n. And that would be considered in terms of m and n. So you're wanting to get rid of all the logs and write your answer something like that. I'm going to give you guys 15-minute head start before we start our next notes. And so you guys through these. I encourage you to work on this part before the graphing part, because this part, understanding this, is going to help with the next section. So I'd work on the second part first. Remember, odd answers on the back. You can even start with odd. I'll put it up there so you can copy it down.